I'm going to introduce a few things about benchmarking, not a lot, because this is, again, this is part of the sort of the old material, if you wish. People in this room, I assume, they're self-selected. They care about performance. So Amdahl's law is a classic. It's used mostly in parallel computing, but it applies to any complex system. Whenever you want to improve a system, you got to start from wherever the action goes, right? It's an obvious law. So if the contribution of one component to the system is 20%, what is the most improvement you can get if you get that to 0? That would be that very 20%. I've seen too many people not in this room, spending time on things like optimizing command line parsing, which is exactly where the first 10 microseconds of your run are going, right? And they optimize for, like, big O complexity. For, how many words do you have in a command line? And that's going to be like, oh, if it's quadratic, it's terrible. It's not. Okay, so collect the profile data before you optimize and focus on optimizing. This is a classic. Choose hotspots from the whole application. And then the interesting thing is profile again within the application. This would be the Ladma's law, which is not a real guy. It's just Amdahl spelled the opposite way. And the trick here is you want to, why do you think you want to do this? So you want to take, focus on the biggest time spender. You want to take it out of the large application, work on it, put it back, test again. Why do you think that would be the case to perform optimization that way? Yes? Shout. You just got to shout. Oh, you just... Okay, so there's no microphones here. Essentially, the simple answer is very often an improvement of 20% come as 9 to 2% improvements, right? So, and you can't do any of these little improvements if you test within the large system because you can't measure it. So you gotta take it kind of you take it out of the application. You have a very good test bed for optimization, and then you improve that little by little by little by little, and then you have a large improvement, and then you can put it back in the system where we can measure. So 20% speed up in an essential component can translate into probably a 5% improvement of the whole application, and that would be great for some domains. So don't forget, the optimizations, of course, may have a variety of global effects, so you can't have the micro benchmark be very telling of what you measure in the whole application. Now, this slide, I'm going to tell you a slide that does not exist. Your coworker, not even your coworker, people at other companies, right? People at your competitors' companies, right? They do the following things. They measure the speed of debug builds. Never measure the speed of debug builds. Yes, I was going into this contest and I went with a snail and it was slow. Yes, of course, it was slow because it was not supposed to be even fast. So do not measure the speed of debug builds. This is a classic, it comes up again and again, so I gotta say it again and again. Sorry, guys. Well, for the other people, that is. It's not for you. Right? Just make sure you propagate the message. Different setup for the baseline and measured, and I've seen sort of a more subtle, mistake that people do. They have the baseline, and immediately after they run the benchmark. And what happens after the baseline? A bunch of things are hot, such as memory and files. If you open a file, you load it, it's going to be buffered in the unused memory on Linux, at least, right? And so essentially, there's a lot of stuff that's happening that the second benchmark is going to benefit from. So if you have your baseline just before what you test, the test is going to be favored. And it happens even with things like malloc. If you malloc a bunch of memory, many malloc calls, and then you have many free calls. So you malloc and you free everything. Do you think you're back to square one? By round of applause, who thinks this is wrong? Okay, one golf clapper, thank you very much. So actually this is very wrong, because by the time you've malloced and then freed a bunch of stuff, the internal configuration, caching, and opportunities taken by the memory allocator are putting it at a completely different state, so the next mallocs are going to be a lot faster. Even ignoring the cache effects, there's going to be a lot of structures that malloc says, oh, this guy allocated 4 kilobytes many times, so I'm going to have like a free list of 4 kilobytes, etc. So there's going to be a lot of preparation that the memory allocator is going to do for the upcoming allocations. So what you got to do is you run the whole process in one way, and the whole process is a different way. Now, there's also things like DNS, so you do a lookup once and then it's going to be cached, and that kind of stuff. How do you guard against files that are opened? So you open a file, you load it, and then you want to kind of make the file system cold. How do you do it? Your Windows. I'm not sure how you do it. I actually on Windows too. Can you unmount things on Windows? Unmount a drive in Windows. Yes, you mount your test files on a drive, and at the end of the benchmark, you unmount it and then you mount it again, and it's going to be cold. It's not so simple, exactly. Thank you very much. Whenever I say always, I say almost always. Whenever I say never, it's almost never, except for situations that may or may not be there. Okay, great. I've seen also mistakes made by people at your competitor companies that they do things like include the cost of printf in the benchmark and stuff like that. Procedural mistakes are changing more than one thing at a time. This is really the first thing you learn as a scientist is whenever experiment, you change one little thing, you measure again. And you change another little thing, you measure again, etc. It's crucial. If you change two things, you have no idea where the improvement came from. Or maybe they could even cancel each other, and then you measure nothing of interest. Optimize rare cases, pessimize others. I have this funny slide, courtesy of Stack Overflow, which was, well, I'm sorting sorted data. And is sorted is actually much faster than sort, because it's sorted, so it's just, So how come sort does not include if is sorted return as the first line? You optimize for a very rare case, which is completely sorted data, thank you, and then everybody else is going to pay for that cost. If you have at least one item that's not sorted, it's going to messed up, right? So you don't want to do that. So, of course, I don't think I need to insist very much that today's computing architectures are just completely intricate and difficult to model even by other computers. So it's virtually impossible to get identical timings for measurements. Whenever you measure, you're always going to get a jitter. So that's why you shouldn't use intuition. For example, a nice intuition would be that fewer instructions mean faster code. Is it correct? Yeah, the right answer is depends, right? It depends, so it's not always the case. Data is faster than computation, so if you cache, you're good. The answer is? Thank you, depends. How do you say depends in Russian? You just shouted the Russian word for depends. Зависче. Not even close, right? Okay, sorry. Data is not necessarily faster than computation. Computation is not necessarily faster than data. Damn it, there's no easy gig in this town. And the only good intuition is I should sit down and time the stuff. That's what's going to make you better than smarter people. If you measure, you're going to do better than people who are too smart to even need measuring. We have a... Oh, thank you. Thanks. All right, so that's going to help you a lot. Now, there are a number of reliable heuristics. With this, we're getting into sort of the new interesting material. So mathematics is good because it gives you a lot of freedom to demonstrate that things are equal, that actually one is more one is faster than the other. Math is interesting because it doesn't tell you, it gives you sort of the rules for things that are equivalent or that are, that have certain properties, but math doesn't tell you that interesting things, what are the interesting things and what are the uninteresting things. Math doesn't care, right? It doesn't tell you, oh, you should, this thing is not interesting, this is interesting. It just tells you, this is like the same as that, and you're like, oh, I don't care about that, but that's interesting to me. So it's really your most important tool. Many people think that optimization is all about doing like machine code and knowing the bits and that kind of stuff. But actually, there's a lot of math in it because you get to prove that that things that are cheap are equivalent. Another intuition that is good, a heuristic, is that computer likes boring. You want to multiply two vectors of 1 billion elements each. Here we go. We have all the equipment in the computer is aligned to do that, right? Do you want to look at some data and depending on what it is, do a regular expression, all that nonsense stuff? I don't like that. That's kind of messed up. So, computers don't like surprises. They don't like things like branching and dependencies and indirect calls. They don't like smart code. They like boring code. They don't like indirect writes. It's something that hardware people have been working at for a long time. It's just an unsolved problem. Indirect is difficult and slow in contemporary computers. Strength hurts. What is strength? Strength hurts. Strength. Which is stronger, multiplication or addition? Multiplication is stronger. The more difficult it is, the stronger it is. What is stronger, power or multiplication? Power, except when it's power of 2, right? So there's also like little exceptions there. But generally, you want to use the least strong operations to achieve a task, and that's where math comes in, right? And small is beautiful. Small plays into a lot of strengths of computers because they like to keep data close and the instructions even closer. So I'm going to, before showing a couple of examples, I want to make a point that Andrei told me is well understood, so I'm not going to insist on too much, but just to make sure that the message gets home. So when people measure speed, they measure, I told you, like, it's obvious to everybody that when you measure many times, you're not going to get the same exact timings, right? So you get a distribution of timings, right? And the usual procedure is choose your experimental conditions, you run the experiment multiple times, and you take the average. Where am I mistaken? Where am I wrong? Average. What's wrong with the average? The average includes the most noise possible because of the way computers work. So almost never a good idea. You know the joke with Bill Gates on a bus in Seattle? When Bill Gates is on a bus in Seattle, on average, everybody in the bus is a billionaire. Right? Which is pretty awesome, but it doesn't make the homeless on the bus feel any better. Right? So this is exactly the problem. In computers, on average, there's going to be always the case that you get an interrupt during what you're doing work. And if you measure something, if you want to measure how fast is multiplication, which is nanoseconds. If you want to measure nanoseconds, you do it many times. But inevitably, during those many times, you're going to have a 2 milliseconds thing because there's the clock interrupt in the middle of a measurement. And are you going to include a sample of 2 milliseconds when you're looking at 6 nanoseconds? Are we serious? Right? You can't do that. I'm not saying you don't do that. People who are, work at your enemy companies can't do that. Let them do it, right? So we know we can't do that. So again, I'm not going to insist on this too much, but don't forget, noise in computers is always additive. It's small for humans, but it's a lot for micro benchmarks. And you're going to capture a bunch of noise by taking the average. So if the average is not good, what is good? Median. What else? What? Standard deviation. No, for some algorithms, it's a terrible thing to do. What? So median is not it. By the way, median is wrong. You don't. What? Worst case. No, because that's the timer. You're measuring how efficient the interrupt system of the computer is. You're not measuring your code. You want to measure your code. You don't want the realistic timings. You want the timings that you can improve. What is the right thing? Well, let's put our math hat right now. So you measure a bunch of stuff, you get a bunch of numbers, and then you look at the density of measurements. Like where did I take most measurements? What time would be with the most density of measurements? Like where did the numbers agree most? Mode, thank you. Who said mode? Right, you earn a hat. Right, awesome. So mode is the mathematical thing to do because it's the point where the most numbers agree, right? So you have a few noise, you have exceptions, you have whatnot, but the mode is where most numbers go. Now, there's a problem. What if you take the mode of quicksort? Quicksort has almost no mode on random data, especially if it's a randomized algorithm. So it depends. If it's a randomized algorithm on structured data, or if it's a non-randomized algorithm on random data, quicksort almost never has an informative mode because the density is like noise. It's almost the same over the whole spectrum. So what do you want to do with quicksort? Yeah, average. So no, you don't take the average. You eliminate 5%, you take the average. Or you eliminate 5%, you take the maximum, that's your P95. Right? That is, in 95% of the cases, I got the time no worse than X. Right? And that's good for networking, for everything where there's randomness, you're interested in things like P95. Because there's definitely always going to be a guy somewhere with a slow modem in a basement who's gonna be like really slow, like 1 hour to download the page. And you know what? You do care about that guy in a human sense, but you can't help everybody. So you're gonna help 95% of the people. So in networking, P95 is a very frequently used measurement. You can't have P100. P100 is not informative. It's one person, really. You see what I'm saying, right? And for quicksort, it goes the same. P100 means the absolute slowest selection I could ever get of the data. It's not informative. It's a corner case, really, right? So, well, I just wanted to kind of make this point that measuring is difficult. And let's get into a few examples, and let's start with replacing branches with arithmetic. You don't want to do if and else on too often, right? But you have to do them. So what do we do? So let's try this. Let me give you the following example, which is a statistical task. But before that, the simple idea is instead of branching, you integrate the result of the branch as a 0 or 1. So the code looks linear now, right? And you have no more if and else's. And you're going to have, you're going to get to the boring case when the computer can just go straight line through the code, as opposed to the compiler wondering what to do next. Not the compiler, the code. So here's a task. Swap the minions of 4 elements to the first quartile of an array. So I have an array, I divide it in 4, and I take the minima of each 4 elements, I put it at the beginning of the array. That way I get statistically interesting data for the first quartile in the first quartile of the actual array. Great. So this is the baseline. Do you guys see the code? I'm not sure if it's, is it large enough? Works? All right, thank you. So let's take the minimum of 4, and we have an array of double. I'm very proud I translated these slides to C# and I actually tested that they do compile. So thank you very much, yes. So what we do is like compute a minimum of 4. It's quite trivial code. So we're taking M, which would be the minimum of I and j, the index of the minimum of I and j, and then we assign it 2 more times depending on the other 2, and then we swap the 2 references. a swap function, I'm not going to implement it. It's trivial, right? It swaps two elements in the array, right, by reference. So nothing spectacular here. So that's my loop. And we have like 4 induction variables in the loop. I iterate the array with 4 induction variables because I need 4 elements at a time. And let's see what we can do to improve things. But first, let me actually talk a bit about how you should test this kind of stuff. Because it's interesting and it's subtle. You want to test it not only on one kind of data. You want to test it on data that could occur in several instances, such as organ pipe. Values go up and values go down. Right? Like in the church, right? It's like in the cathedral. Random that's random data, uniform. Random 0, 1, what do you think it is? Random 0, 1. Random zeros and ones. What's the difference between random 0, 1 and random? There's a bunch of duplicates, right? So that's important. There's a bunch of duplicates. Random data, it's duplicates, but hard to predict duplicates, right? So that's another important case. Sorted is already sorted data, and then you want to take some data from an actual measurement of a physical measure, which would be real data. And these are your testing sets. So there are a few typical artificial data sets. There are a few uniformly distributed data sets, and then you have a real data set. And this is how a serious measurement should go. You should kind of think in advance about what kind of data you want to measure stuff with. And these are actually generally accepted in the algorithms community. Great. So pass number 1, and I'm gonna just let's improve this code for performance. So personal sense and sensibility, just try to not repeat operations too much. So I'm going to pre-compute n by 4, n by 2, and 3, n by 4 in those integers I, j, k, l, and l. And I'm going to just use them inside the loop. So I'm going to hoist a few computations outside the loop. Actually, it turns out that computations were not my main problem. I don't get faster code, but I do get smaller code. So there's a bit of a win. Maybe 0.5%, right? So, okay, so the research goes on. Number 2 is let me reduce the dependencies across the data. In the first approach, let me go back one slide. In the first approach, you see, we had this computation of m, which with a minimum index of I and j, but then m is going to be assigned potentially 2 more times. So the computation of m equals k and m equals l, they depend on the previous computations, right? So I'm going to have m is going to depend on its own previous value, right? So we want m to have fewer dependencies. So what we're going to do is compute m0 and m1, right? We're going to compute 2 comparisons in parallel, and those are going to be swapped at the end. So I compute the minimum of I and j and the minimum of k and l, and then I'm going to proceed with swapping depending on the comparison of m0 and m1. So far, so good. I was very hopeful. I thought, oh, this is going to be like twice as fast because it's all parallel and nice. It's actually same speed. So I didn't improve things any. But I think reducing dependencies is generally a good thing, so I kept this code. So that's why it's important to kind of have all these heuristics and attempts and stuff. And here's pass 3, which is let me actually reduce the number of induction variables. Instead of I, j, k, l, let me just use I and then use arithmetic to compute the other 3. Because they're in a constant relationship with each other, right? So no challenge there, so I compute m0 from, instead of saying k, I say I plus q, and I say I plus 2 times q, and I times 3 plus q. I plus 3 times q, right? So that would be my, my approach to reducing the number of induction variables. I was very hopeful about that too, but as it were, if you measure, you're not going to get anything. That's why it's important to measure. Everything I told you, if I didn't have measurements, I could have bragged that the performance is better, and I had good arguments to say so, but actually it would have been a lie. That's why it's very important that you have good measurements in place, good benchmarks, you have a good test bed in place that's going to tell you where you're going. All right. Pass number 4, multiplication by 3 is awkward. Let's get rid of it. So I'm going to do, instead of 3q, I'm going to do things like q plus q, and I'm going to restructure the loop to get rid of multiplication by 3. And I got a whole bunch of like 3%. Nothing to write home about. More ideas. Let's get ideas. Sorry? Remove the ternary operators. Yes. All right. So to do so, I actually have a more general proposition for you. What does this function return? Optional. I give it a Boolean and an integer. And it does the following. It converts the Boolean to an int32, and then it takes the bitwise AND against that guy, and there's a minus in front of it. What the hell is that? So let's see. Level with me. If flag is false, what's going to happen? 0 minus 0 is 0. Who the hell cares? 0 and 0 is 0. I get a 0. If the flag is true, 1 minus 1 is... Huh? What is minus 1 in 32? F, right? It's all F's. When I AND all F's with something, what do I get? That guy. So by this simple formula, you have a way to say, I want an optional value or 0. If the flag is false, I get a 0. If the flag is true, I get that value. And there's no if. There's no test. It's boring. It's boring for the computer. For us, it's like, oh my God, that's kind of cool. Like minus, convert, all that nonsense. Okay, good. Awesome. So let's try this guy. And I'm going to say, instead of the ternary stuff, I'm going to use optional, and I'm going to integrate it within the computation. So I use it 2 times, and I still keep the question mark at the end. So I have, instead of 4 tests, I have 1 in this loop. So let's measure this guy, because this guy is where things get interesting. All right, so that's why it's important that you measure on many data sets, friends. Because if I only measured on 1 data set, I wouldn't have seen anything. It's 16% slower on organ pipe. Nothing interesting. It's 18% slower on sorted. But it's over 2 times faster on random data and on real distributions. And the question to you is, why the hell is that happening? Ideas. I just, shout at me. Say branch prediction in Russian, everybody. 1, 2, 3, go. No, in Russian, man. All right, so in the case of sorted data, the branch predictor is going to do pretty much no interesting jumps. So there's no surprise for the branch predictor. It's going to predict with 100% accuracy. In the case of organ pipe, how many failures am I going to have, fail predictions am I going to have? 1 at the middle, right? Ridiculous. Very, very few. Maybe 1 at the beginning, 1 at the end, 1 in the middle, and 1 at the end, and we're done. There's like a tremendous rate of success, right? So the branch predictor has no trouble picking up easy data. But when you're random data, the difference is huge. And it's huge because you replaced all of these unpredictable tests with what? With simple logic. And so getting back to some fundamental truth, what are computers good at? They're good at computing. And this is kind of an interesting reality, because they're not good at branching or drawing things on the screen. They're good at computing. They're best at doing what, and minus and that kind of stuff is like, oh yeah, I'm a computer, I know how to do this. Branching, yeah, I could branch it for you, but it's kind of a mess, So now, okay, I'll do it for you, but whatever. Right? So it's not something that computers do naturally. What they do naturally is computation, and this is computation, right? Okay, so with optional, we got a huge win on real data and on random data, on interesting data, as it were. So that's a nice result. And we can take it even further, and guess what happens here? Here I'm going to use optional 3 times instead of 2 times. And here I got like, just a bit of a smaller gain. And why do you think that's happening? The gain was not so big. Why do you think that's happening? At this point, you got to look at the generated code, which is where Sasha is going to take you. Not with this example, but Sasha shows you like exactly what the hell happens because he shows you the generated code. And if you look at the generated code, you're going to see an interesting thing. You're going to see that in the previous code, with the question mark, the compiler already figured out a way to do it branchless. So the compiler was smart enough, he can say, I don't know what the hell is doing with it. The optional thing, okay, I'll inline it for you, whatever. And then it goes down to the question mark and says, there's a test here, so I can work it out. So the compiler works it out. So then if I use optionally instead, it's just going to be slightly less good code. So that's why it's important to measure, right? Great. I didn't get this particular function to register gains with this particular example, but I do recommend the following function. If else branchless, which was the following way. What if flag is 0? What's going to happen? Well, I take it as 0, I convert to int 32, and that first line there is going to be a 0, right? And then I take a convert to int 32 of 0 minus 1, which is going to become, right? It's going to become all Fs, and then I end that with bitwise with the value, the second value, V2, and then I'm going to get that guy. And all of these, both of these are ORed, so I'm going to get just V2. V2 or 0, which is V2. Now, if flag is 1, I'm going to have exactly as we discussed on the first branch, and in the second case, I'm going to have convert to an int32 of 1, which is 1, minus 1 goes to 0, and that particular, the bottom line is toast, is 0. And or 0 is something you get V1. Make sense? So this is a branchless if. My hope is that somebody who's doing backends is going to see this, because for some reason, contemporary compilers don't do this kind of stuff yet. They should. They should do it for me. Why shouldn't they, right? You still discover these cases in which they don't do it for you, so you got to do your little math there to make it work. Truth be told, once you have these functions, you can redesign your entire algorithms in a way that the compilers can't figure out for you, because you're smart. The compilers are not. No offense intended to compiler writers, but you're the smart person here who is creative and can rearrange the algorithms altogether, redefine them in clever ways. So that's a branchless ternary operator that you can use. Great, so I tried this. It's actually not so good in this particular example, but that doesn't mean much because there's so many other cases in which you can use it successfully. And now let's switch gears for a bit. I have 20 minutes to go. This is awesome. Large set intersection. So now we discussed like and minus and these things. Here we're going to discuss designing entirely new algorithms. Like, open your mind. There's no tricks. There's no kind of itsy-bitsy things. We're talking about like grand things, redesigning entire algorithms. So let me tell you about the set intersection algorithm. Did you ever see this merge sort? Merge sort, okay. Multiply two vectors, right? Find the common elements of two sorted vectors, right? That kind of stuff. So I'm seeing like, I like it that I see kind of complementary hands being raised. Like some guy raised his right hand first and then his left hand, and that was great. So I assume that this is kind of a known pattern. So I'm going through two sorted sets, and whenever I find something equal, then that's a match. If this guy is smaller, what do I do? What do I do if this guy is smaller than this guy? They are sorted. Yeah, bump this guy, right? And if this guy is smaller, what do? Bump this other guy, right? So they kind of follow each other, and you're going to find matches in sorted sets. And it turns out this simple algorithm is fundamental for a number. You may claim it's the most used algorithm in the world. Like literally, because whenever I search for a multi-word query, it's going to run. Google runs it. Like every multi-word search, it's going to be a set intersection between two sets. Right? So it's amazingly useful. And this comes again and again and again, and it's a popular interview question. So I was laughing with Sasha last night that he got this interview question at Google, and oh, wait a second, that was my interview question at Facebook. So isn't it a kind of a strange coincidence that all of these big data companies ask you the same questions? You have this at Microsoft, thank you, Azure, right. Any other takers? Who gives more? All right, so let's actually look at this closer. So it's used in dot product. We mentioned all of these. It turns out all database queries must use it as well. And it's all of these like pattern matching intersection stuff. Great. So the basics. Well, we discussed this with the bumping and everything. And let me show you the baseline. In the baseline I have, well, if both are empty, there's nothing interesting, I return a 0. And then I'm going to proceed with this odd infinite loop. And as I said, I'm going to do the increment and the break and stuff. And if in the nice case, the match case, I increment the result, and I'm going to test again for the end of the loop. By the way, why don't I put the test at the top of the loop? Because I could say 4 instead of the infinite loop, which is kind of idiotic, right? I could put 4, until I1 is less than length and I2 is less than the other length. So why don't I do that, friends? Because it would be redundant work. You see, on the first branch, I'm going to have if A1 of I1 is less than I2 of I2, I increment I1, and I only need to test that guy. If I increment the second I2, I only need to test that guy. And only in the third case, I need to test both. So if I put a test at the top, I'm going to do useless work. I'm going to test things that don't need to be tested. Right? Bigger code, slower code, right? So great. So this is our baseline. Let's make it better together. Right? So what is the complexity of this function? Complexity, big O. It's linear in the sum of the two, right? In the lengths of the two inputs, right? Linear. It essentially takes, that's the worst case complexity. It turns out it's also the average complexity, right? Great, linear. It turns out in machine learning, very often you need to intersect sets that are very different in size or different in statistics. You have a long input vector and you have a short feature vector that you test against. Think of this. A1 has 1,000,000 entries. A2 has 1,000 entries. Are you willing to pay 1,000,000 steps for that stuff? Are you willing to walk 1,000,000 steps to that stuff? Probably not. Where would the time go if A1 has 1,000,000 elements and A2 has 1,000 elements, in the worst case? Where does the work go? So tell me the line. Which line? Which is the hottest line? Which is the red line here? If plus plus A1 equals a dot length break. Is that right? I do a comparison if A1 or I1 less than, right? I do a comparison and increment. Comparison and increment sounds like a damn linear search. Doesn't it? What I do is literally I do linear search in the long vector for the elements in the short vector. This is what happens. In the worst case, I'm going to do repeated linear searches in the long, not repeated, but kind of slowly progressing linear searches in the long vector. So that's kind of bad, right? So how do we improve it? Well, if not linear, binary is better. So let's use binary search, right? So binary search is nice because it gives me the index of the, the rightmost index of the things that are smaller. So I'm going to have this implementation. So you take this to production and measure it, it does B search, and it's not very good. When does this implementation work badly? Not too well. What's the worst case for this thing? B search fails every time. When does B search fail every time or kind of return something at the edge? It's in some very useful scenarios. One is identical inputs. If you have two identical inputs, you do like an idiot binary search when all you should have done was the first algorithm. Right? So why would you do binary search when it's right there, man? It's right in the left-hand side. It's right there, man. It's the first element you're going to ever look for. So actually, a binary search is slower than just simply doing the classic algorithm with linear search for some really good use cases. So A1 is a short affix of A2, same discussion. Yes? Question? Okay, I was hoping I was... Okay, so that would be a bad case. Let me take suggestions from the room. Ideas. Ideas, yes. Ideas, thoughts. How to make this work on identical data and on not non-identical data just as good. We want the best of both worlds. Yes? Check the first element first. Is that? Oh, check all data. Probably that's going to be a large cost up front. Just check the sizes. They may be slightly different. I'm talking not identical data. I'm talking almost identical data and data with very similar statistics, right? When one vector is a prefix of another. Check the next couple of elements. Yeah, take a look and make a little speculation there. Thank you. Other ideas, thoughts? What? Yeah. So make the portion search smaller with each search, and that's actually I'm not calling you Captain Obvious, but it's a Captain Obvious kind of idea. Whenever I have a search, whenever I do a binary search, I find the position, and then everything to the left of that guy, I don't care for, because remember the other vector is also sorted, friends. Come on, be with me, join me. Right? This is awesome. So I do a binary search, I find an index, everything is greater than, everything is less than, but this guy is also sorted, so whatever is less than, I'll never find it ever. So I can drop it. So that's the Captain Obvious improvement, right? So with every search, I'm going to reduce the data searched with binary search, right? So what that is doing, I'm gonna, I don't show B search, it's easy. But essentially, I'm going to be searching the portion of A2 that starts at I2 and ends at A2.length. So I'm going to reduce the portion searched by, by increasing I2 with every search. Other ideas. Okay, let's try this, whatever, it's still not good enough. Other ideas for making this faster and better. Don't forget, Google wants you to come with ideas, thoughts. Better, do this better. So we want linear search when it fits. We want binary search when it fits. Yes? Okay, so kind of swap them so you always have, for example, A1 is the shorter one. And then you focus on that case. So let's focus on that case, and then, so that's definitely a step forward. And then let's say A1 is short, A2 is long. Yes? Vector instructions, SIMD. Actually, SIMD may be slower than binary search, right? So it's kind of a discussion, right? How much data you have and stuff like that. So I would contend that going for the right big O complexity is the right way. Yes. Yeah, so you do a little speculation. You look at the leftmost. Okay, so I have good news for you, friends. You're getting like really close to a very interesting algorithm, which is called galloping search. And it was invented by a Russian. I think Jewish Russian, I don't know, but it has a Russian name. So galloping search it's a binary search, but it has a different schedule. With binary search, you start in the middle like an idiot. When you look in a phone book for a name, are you going to crack it open at the middle of it? Probably not. You're going to say, his name is B, whatever, Bogdan, so I'm going to open like somewhere in the beginning, right? This goes with the following idea. My search is a binary search, but my schedule is I'm going to start from the left-hand side with a step of 1. I don't find the guy. And I'm going to look at the next element. And then I'm going to increase the step to 2. Careful here. I don't find the guy. My next step is going to be? Who said 16? Okay. You're fast, young Padawan, so not yet. My next step is going to be? Let's hear it. Chetiri, right? Chetiri. So it's going to be 4 because I'm exponentially increasing the step. That's how I get the good big O complexity, right? What if you increase it what if you increase the step linearly? What complexity do you get? That's also an algorithm. It's a different algorithm. And it gets you square n search speed. But we don't square n when I'm fast. So we're going to increase the step by exponential schedule. We're doubling it with every time. And whenever we overshoot, what do? Look on the slide. What do you do when you overshoot? We revert to a classic binary search in whatever is left. That's kind of end game. The time doesn't go there. The time goes in the first. So now you have identical, so all of the speculations that you proposed are going to be incorporated in this nice algorithm, right? Because you're going to do the speculation for the first element, for the second element, for the fourth element, right? And if it's the third, you just have to do one more step, one more comparison, you're done, which is amazing. So if anything is close to the beginning, then it's great. So awesome. And with this, we're going to have a real good solution. So that's really the best of both worlds. Because you simply replace binary search with galloping search in intersect. You start the search on the left side, and it just works. Then you can, we discussed this a bit. So continue with exponentially increasing steps, and when overshooting, you go back to binary search. And the complexity is good. Who knew about this algorithm, by the way? Okay, so I'm glad to convey new information here. So now let's discuss a bit scaling up. We have a few minutes left, so we can discuss scaling up, which is I want to intersect more than 2 sets. So I want to do everything we discussed, but there's k sets. Because when you search Bjarne Strustrup, Herb Sutter, Scott Myers, it's going to have to intersect all of these names, right? Sorry, I'm in the wrong conference here. When you search Anders Hallsberg, right, and other luminaries in the C# community, you're going to have to intersect all of those sets. Whenever you do a multi-word search, there's going to be a multi-set intersection. Thoughts, ideas for how do we do multi-set search? More than 2. Yes, thoughts, shout. Test the first 2, and then the other with the next, and so on. That's a possibility. It's not the best, actually. There's other possibilities. What response did you give to the interview question at Microsoft? What was? Okay, long time ago. So, another possibility is you're looking at the leftmost element of k arrays, right? The leftmost element, and you want to find the minimum. So that guy you're gonna have to bump, right? If only there were a data structure that allows us to get the minimum of many elements in constant time. This side says heap. What does this side say? Huh? Heap, yes. Heap, friends. So you organize, it's a weird heap because it's not a heap that has a physical array under it. It's an imaginary heap, it's a structural heap. You just organize the leftmost elements, you organize them in a heap. It's a vertical heap, right? And you keep the minimum, and that's your easy way of dealing with things. So you extract from that heap, you extract the shortest element, and then you can search in all the other sets and stuff like that. So actually, it turns out this is quite a cottage industry. In practice, you have several sets, and it turns out a lot of papers are dealing with that case. And I'm going to give you a few pointers here. SVS would be sort of the classic algorithm, which was mentioned in the room. You actually group the sets and you take the two smallest ones, and then you have a candidate as the shortest set. But there's actually a lot of papers, and there's a good overview at the linked site here. It turns out it's an increasingly interesting problem to work on. This pattern of set intersection, dot product of sparse vectors, merge sort, finding common, pattern matching of any kind. So this turns out to be a very useful algorithm, and I'm very happy to be able to share it with you. With this, I'm done. Thank you very much. I know there's there's like a torture room with questions and stuff, but I can take a couple of questions right here if needed.
Raise your hands, please, in case you have any question.
Hands up. Yes, please.
Hello. So I saw we were speaking about several kinds of sorted data. So cathedral data, 0-1s data, and complete randomness. So let's imagine I have several unit tests that cover all these kinds of data, and one day I see that my one test degraded, for example, 0-1 test, and what does it actually mean? So my real data test still working fast, everything else working fast. Should I be
worried?
Yeah, worried, or maybe it is okay, because if my real data test is working fast enough, I probably can get rid of all those other tests.
Thanks. Thank you for asking, and I'm very glad you asked that question. So let me repeat it first just to make sure I understood. So let's say you have unit tests, and you have like performance tests, you have regression tests, and it turns out your application, after some changes, so you kind of run them continuously or every once in a while, your application has degraded performance on one of these artificial data sets, right? Thank you. But it turns out on real data, it keeps on working fine. And the question is, should I worry or not? And actually, there is a meaningful answer to this. So, the classic answer would be, well, it depends, all of that kind of nonsense that consultants say, right? But there is actually a meaningful answer, which is the following. You should worry. You should worry. I noticed, so I worked at Facebook for the better of 6 years, and a large part of that in high-performance applications. And it turns out whenever you have a regression on artificial data, it turns out that's a harbinger of worse things to come. It's almost always a predictor that things are going south. Things are going worse, and it's not a good situation to be in. So you should be worried, because that usually means you have an inefficiency hidden in your code that's going to be only amplified by further changes. It happened to us at Facebook quite a few times to have, and it works both ways. If you have just a small improvement, you should be happy, because there's only this much that sometimes 1% plus 1% is really 3.5%. It could happen, right? So if you have a small improvement on a certain case and stuff, you should be happy, because something's going to give. These things are going to kind of add up. And similarly, when you have a small degradation, maybe you still have a degradation of real data, you can't measure it yet. But then you kind of keep on going with that code, and it's gonna only degrade even worse. So I would advise people to, whenever they have decrease in performance on artificial tests on typical, your typical artificial data, I think you should be worried and should look at what's going on. Questions?
We run out of time, sorry.
We're out of time.
But still we have a discussion zone.
Yes.
Straight ahead and to the left from the room. And, ребята, давайте еще раз поблагодарим Андрея и Alexandrescu.
Thank you very much. Thank you. Thanks.